Hello guys, good evening. Can you hear me all? Okay. Few minutes will start.
Hello? Hello, sir. Can you hear me? Sir, can you hear me?
Yeah.
Okay.
Do you know somebody called Tanmay? Okay, what's his full name? Yeah. He's from KRM, right? Ansh. Okay, fine. So what have we done last class? I think we have finished the concept of limiting reagent, right? Yeah. So we have discussed about the limiting reagent, and limiting reagent is the reactant, one of the reactant molecule which gets consumed completely to give the maximum amount of product. Okay. So limiting reagents consumes completely in the reaction to produce maximum amount of product. This is what we have discussed. We have also discussed how to find out limiting reagent, right? Right. Let's see one question on this. Try this one. 0.5 mole of CaBr2 is mixed with 0.2 mole of K3PO4. The maximum number of moles of this can be formed. Write down the reaction first, guys. Okay, Kshitij is getting A. Okay, Pradyun is getting B. Okay, so Pradyun is also getting A. Let's discuss this question. Okay, fine. 0.5 mole of CaBr2 is mixed with 0.2 mole of K3PO4. Okay, so let's write down the reaction first. CaBr2 plus K3PO4 gives, it forms Ca3PO4 whole twice plus KBr. Okay, if you balance this reaction, we have 3 here, 3 Ca, phosphorus 2, so we'll write down 2 here, 6 potassium, so 6 we have here. I think it's balanced. 4 into 2, yeah, it's balanced. Okay, now what we can say that 3 mole of CaBr2 combines with 2 mole of K3PO4 and forms 1 mole of Ca3PO4 whole twice. Okay, it says 5.5 mole of CaBr2 is mixed with 0.2 mole of K3PO4. Okay, so what we are taking, like I told you already, that the initial number of moles will be given. If you want to use limiting reagent concept, the initial number of moles will be given in the question. So this one is given 0.5 mole and this one is given 0.2 mole. We need to find out with these many moles, 0.5 and 0.2, how many moles of Ca3PO4 whole twice obtained. Correct? So obviously when you look at it, the limiting reagent is K3PO4. Right? We can easily find out it is 0.2 by 2, that is 0.1, 0.5 by 3, that is more than 0.1. So this is a limiting reagent. So 2 mole gives 1, so 0.2 mole gives, right? 2 mole gives 1, half of it. So 0.2 mole gives 0.1 mole of Ca3PO4 whole twice. The answer is option A. Easy one. Okay, one more question you see. (20 grams of NaCl reacts with 50 grams of AgNO3. Calculate the amount of AgCl formed. Try this one. Yes, what is the doubt? 20 grams of NaCl. Achha, answer is 20 grams you are getting. Are you getting 20 grams? No, it's not. It's blunder that you have done. I understood what you have done. It's blunder. You cannot do that. It was not at all expected, guys. See what you have done. Now just wait and listen to me, all of you guys. Just wait and listen to me. Just a second, all of you. What I can understand that what you have already done in this question, like Oro and Pradyun, is this. The reaction is this: AgNO3 plus NaCl, it gives AgCl, right? Plus NaNO3. That is what the reaction we have. And what you have done, I think you have done 20 grams of NaCl gives 20 grams of AgCl. That is what you have done. 1 gram, 1 ratio we have. Hence, you have done this, right? That you cannot do, guys. That you cannot do, because these are the molar ratio. We can say 1 mole of AgNO3 combines with 1 mole of NaCl gives 1 mole of AgCl. Mass you cannot compare like this, right? You cannot compare mass. Mole is fine, mass you cannot compare. You cannot say 20 grams of this gives 20 grams of AgCl, but mole you can compare. By this reaction, you can say 1 mole of this gives 1 mole of this. Are you getting it? Yes. What is the gram of NaCl? Now, molecular mass of Na is, atomic mass of Na is 23. For chlorine is 35.5. For silver, it is 108. Atomic mass of silver is 108. Nitrogen is 28. Oxygen is 16. 41.6 is close, Shitish. Not correct, but close. Chlorine is 35.5 and sodium is 23. .18. Yeah, that's correct. 42.18 is correct. No, 39 is not correct, Gurman. Okay, so first of all, guys, what we have to do here, since we can compare the molar ratio of this AgNO3, KCl and this given mass, we have to convert into the number of moles. Okay, so these many mass, like what is the mole of NaCl? 50 gram of AgNO3, what is the mole of AgNO3, right? So reaction is balanced, nothing you have to do. 20 gram of NaCl, this 20 divided by the molecular mass of NaCl is 58.5. These many moles of NaCl we have taken initially. AgNO3 is 50 gram divided by molecular mass of AgNO3 is 108 plus 48, that is 156. 156 plus 28 will be 174. 174. Oh, I'm sorry. It is 170. Atomic mass of nitrogen is 14, right? Yeah, it's 14. So 16 into 3 is 48. 48 plus 14 is 62. 62 plus 108 is. Are you getting 170? Is this correct calculation? These many moles of this we have. Okay. So now, first of all, the question is simply based on the limiting reagent. So we need to find out which one is the limiting reagent. How do we do that? Okay. So it is 5 by 17. Okay. This value is 5 by 17 moles of this. And when you solve this, it is 4 into 5 divided by this 15 point something. Okay. So which is the limiting reagent? Limiting reagent is AgNO3. Right? When you solve this, you'll get 5 by 14 point something. This value is 5 by 14 point something you'll get, which is obviously more than this value because here in the denominator we have 17, correct? 14.6 approximately you get. So this is the limiting reagent. Hence 1 mole of this gives 1 mole of AgCl. So 5 by 17 mole of this gives 5 by 17 moles of AgCl. Now this is equals to mass of AgCl divided by molecular mass of this, which is 108 plus 35.5. Now with this, if you find out mass, you'll get approximately 42.2 gram as the answer. Correct? All of you understood? So you cannot compare mass directly. Okay. Sometimes the question that they ask in terms of mixture, percentage composition and all, we need to calculate. So look at this question based on this. Write down 4 gram of a mixture of CaCO3 and sand. Sand is nothing but this SiO2, silica, we also call it as, is treated with an excess of HCl and 0.88 gram of CO2 evolves. Okay, you need to find out the percentage of CaCO3 in the mixture. Try this one. Percentage of CaCO3 in the mixture. Okay, you see the the mixture of CaCO3 and SiO2 we have. SiO2 does not react with HCl. It is a reaction of CaCO3 and HCl, which gives CaCl2 plus H2O plus CO2. Try this now. Okay, Ansh is getting 50%. Let others also try, Ansh. Okay, right. You see that the catch in this question is what? That what is a reaction? That is it, right? So you should know this fact that this SiO2 sand does not react with HCl. This you should know. HCl. Hence, the only reaction possible is what? Reaction of CaCO3 and HCl. CaCl2 plus H2O plus CO2. Now we'll balance this reaction first. Is it balanced? It's fine now, correct? Yeah. So 4 gram of mixture of this excess of HCl gives this gram of it. Okay, so what we can say, 1 mole of this, right? 1 mole of CaCO3 gives 1 mole of CaCO2, sorry, CO2 gas, and 1 mole is nothing but for CaCO3, it is 100 gram of it. So for CO2, the mass is 44 gram, means 100 gram of this gives 44 gram of this, correct? So what is the mass of this we should use so that the mass of CO2 is 0.88 gram. Okay, so we can do this in 2 different ways. We can assume the X mass of this gives 0.88 gram, right? Then we can easily say that 100 gram this gives 44. So 1 gram of this gives 44 by 100 and X gram of this gives 0.88. So this is a relation. You can find out X from this, which is nothing but 2 gram. The mass of CaCO3 is 2 gram. So out of 4 gram of this mixture, 2 gram is CaCO3. Then the percentage of CaCO3 is obviously 50%. Okay. Another way what we can do, another way is what? We can also do this way. 0.88 gram of CO2 is equals to 0.02 moles of it, right? So 1 mole of this requires 1 mole of CaCO3. These many moles required, the number of moles of CaCO3 is equals to 0.02. This is mass divided by 100 molecular mass of CaCO3. So that would be what? 0.02. Again, you see the mass that we are getting here is 2 gram. Both way we can do. Either you can do by this method, alternative method is this, or you can do by this increment. Is it clear? No doubt. One more question on this. A reaction is X gives 3Y plus 5Z. 3Z gives 3P plus 5Q. And 8Q gives 7R plus 8S. The question is calculate the number of moles of S produced if 5 moles of Y was produced. Try this. Done? Okay. Okay. I'm getting different answers this time. 2.78, 125 by 9, 14, 5, 14 again. 5 by 3 moles. Again, one another answer. Okay, guys. So let's do this. Just a second. Okay. So first of all, your question should be whether this reaction is complete or not. Right? When you get this kind of questions, one assumption is there that the reaction is complete and balanced. Okay, that is what assumption we should take. Okay, so it should be given in the question, but I wanted you to ask this, sir, how whether this reaction is balanced or not. Okay, but there is no other way. If you do not assume this reaction to be balanced, this is Z, right? You cannot do this question. So first assumption we are making here is what? That the reaction is complete and balanced. Now, the question is what? The question is we need to find out the number of moles of this S produced. This we need to find out. If the number of moles of Y is given, this is given, and this is 5 moles. Okay, you see this is series reaction. The product that we get in first reaction, that product becomes the reactant of the second reaction. Similarly, one of the product of the second reaction becomes a reactant of the third reaction. So this kind of reaction we call it a series reaction. So we are starting from this and we are getting this. We need to find out the number of moles of this. Okay, so assuming the reaction is balanced, so what we can say, if 3 moles of Y we get from 1 mole of X, and this 1 mole of X only, it gives 5 moles of Z. Right, so what we can write here, 3 moles of Y is equivalent to 5 moles of Z. Or we can also say 1 mole of X gives 3 moles of Y and 5 moles of Z. Is it correct, guys? Still here, any doubt? No, right? Yes. Next. So, first of all, since this, to find out this, we need Q. To find out Q, we need Z. And Z we can calculate from the first reaction. So 3 moles of Y is equivalent to 5 moles of Z, right? So 5 moles is equivalent to how much? So if I write down here the number of moles moles of Z produced is equals to 3 moles is 5, so 1 is 5 by 3, so 5 is 5 by 3 into 5. Is it correct? 25 by 3 moles of Z produced. This mole we are using here. We have 25 by 3 moles of Z. And what is the moles of Q we'll get here? 3 moles gives 5. So 1 moles gives 5 by 3. So these many moles gives how much? So here if I find out the number of moles of Q is equals to 3 moles gives 5. So 1 moles gives 5 by 3. So this moles gives 5 by 3 into 25 by 3. That would be 125 by 9 moles of Q produced. Now here we have 125 by 9 moles of Q. So 8 moles gives 8. So these many moles gives what? These many moles of S. So number of moles of S equals to 125 by 9 moles of S. Is there any doubt? Correct. Okay, so these are the few questions we have discussed on limiting reagent. Okay, various types of different types of questions we have discussed. Okay, and you will get questions like this. Little bit of prior information you should have regarding the reactions, like the one reaction we did, that percentage composition reaction. Okay, CaCO3 and silica. So you should know this fact that silica does not react with HCl. So when you solve some questions, you'll get to know about these facts. Okay, that you should keep in mind. Okay, can you go to the next part of it? All of you. Correct. Now the next concept we are going to discuss here is principle of what if you replace Z and Q in the first reaction? Let us go to the next, the previous slide first. Your doubt is what, Kshitish? That what if we replace Z and Q in the first reaction? Z and Q. Where is Z and where is Q? Like this. This should be here and this should be here.
No, sir. I mean, what if you
we don't have Q in the first reaction, Kshitish.
Sir, I mean, what if you simplify the second reaction with 3Z?
This should be here and this should be here. That is what you're talking about, right?
No, sir. I'm saying, so if you divide this whole reaction, the second one, by 3.
Okay. This by 3, this by 3.
Yeah. So this will give Z gives P plus 5 by 3Q.
Correct.
So then you can replace that in the first reaction. So what if you go in that way? Do you get the same answer?
Yeah, that way also you can do. In that case, what we can write? 1 mole gives 5 by 3 moles of this. So these many moles gives how much? 5 by 3 into this. Molar ratio, if you are dividing this 3 in all these reactant and product, that won't change your answer. because it's still the molar ratio is same. But mole calculation is same. 3 moles gives 5 moles of this. So 1 mole gives 5 by 3. That is what we are calculating. 1 mole gives 5 by 3 of Q. So 25 by 3 moles of this gives you what? 5 by 3 into 25 by 3. Okay.
Okay, sir.
If you change this, suppose here it is 3. Here you write down 3 by 2, 3 by 2 and 5 by 2. Then also it won't change. Because molar ratio is still same. Right, 3 by 2 gives 5 by 2, so 1 gives 5 by 3. Right, so if you're doing the change in all the reactant and product, right, and you are maintaining the molar ratio of this, then the answer won't change. Randomly, if you write down this, see, if you write down this 2 moles of this gives this, then your answer will be different. Because this is a different reaction altogether. Since you have changed the stoichiometric coefficient. Got it?
Yes, sir.
Yeah, so here it is 3 only. Okay. Fine. The next concept we have to discuss here is, write down, principle of atomic conservation. See, this concept we use when the reaction is not given. Or suppose by any means, if you are not able to balance the reaction, then we can use this concept. If we can balance and initial number of moles is given, then we'll use the concept of limiting reagent. Okay, so write down in this first. In a chemical reaction, the number of atoms of each element remains conserved. Right? The number of atoms remains conserved. Listen to me very carefully here. We'll apply this principle of atomic conservation for the atoms of each element. It is not for molecule. Suppose we have a reaction CaCO3 is present over there. Right? CaCO3 on heating it gives CaO plus CO2. Right? So what we can write? We can write the principle of atomic conservation. For calcium we can write in this reaction. For carbon, we can write in this reaction. For oxygen, we can write in this reaction. It is not like principle of atomic conservation will apply for CaCO3, not possible. Okay, we apply this for atom. That is what the name suggests. Principle of atomic conservation. We conserve each and every atom in a chemical reaction. Okay, so let us understand this by the simplest example we have. And we are taking this example only for the reference. N2 plus H2 gives NH3. Now you will say, sir, we can balance this reaction and we can find out we can do the calculation, right? Okay. But what I am suggesting you to understand this concept, let us assume for a few minutes that you do not know how to balance the reaction, right? Balancing of reaction, you do not know. Let us understand this now, correct? Now, since the reaction we do not know how to balance and initial moles is not given, but you know the fact that the atoms in a reaction remains conserved. Means what we can say, the number of atoms of nitrogen on the reactant side is equals to the number of atoms of nitrogen on the product side. This statement is true for hydrogen also. The number of hydrogen atom on the reactant side must be equals to the number of hydrogen atom on the product side. Is it clear? CLR. CLR. I want this CLR from all of you. Quickly, guys. No, it's not equal. It's conserved. I said it's, yeah, I'll repeat many more times. Okay. I said it's conserved. Number of atoms this side is equals, is, you know, on the product side, total number of atoms will be same. Okay. It won't change. Total number of atom this side is equals to the total number of nitrogen atom this side. Total hydrogen atom this side equals to the total hydrogen atom this side. Now, how to do this calculation, you see. Since the number of moles is not given, so what I'll assume, because in the first case, no, wait, just a second. I said it should be, the reaction is not balanced. You cannot do that, Kshitiz. I said it should be balanced. It should be equal. That's why we always write down the reaction N2 plus 3S2 gives 2NS3. But we do not know how many atoms of hydrogen we have this side and that side. We do not know. Correct? Right. So this reaction is given and initial number of moles is not given. So obviously we cannot apply the concept of limiting reagent here, because LR concept we only apply when initial number of moles is given. So what we'll do, we'll assume, and what we assume, the initial number of moles of this. I am assuming X moles of N2 we have taken and Y moles of H2 we have taken. This is the assumption. Now, could you tell me how many molecules of nitrogen we have on the reactant side? Number of molecules of nitrogen on reactant side. How many molecules? How it is 1. I said X moles. So we know in 1 mole we have Na molecules. So in X mole we have X into Na molecules. Any doubt? Right? Number of molecules of hydrogen on the reactant side. Again, it is Y into Na. Any doubt? No. Right? X moles of this, Y moles of this. Now we'll apply POAC. We'll apply POAC for each and every atom one by one. First of all, I am applying for a nitrogen atom. POAC for nitrogen atom. Okay, nitrogen atom. So we have to count the total number of nitrogen atom this side and total number of nitrogen atom this side. So for this, I am also assuming we have Z moles of NH3. Number of moles basically we have assumed X, Y, and Z. So number of nitrogen atom on the reactant side is what? One molecule has 2 nitrogen atom. So these many molecules will have X into Na into 2 nitrogen atom on the reactant side. Yes or no? Nitrogen atom on the reactant side. This should be equals to the nitrogen atom on the product side. So Z moles is equals to Z into Na molecules, and 1 molecules of ammonia has 1 nitrogen atom. So this into 1. Further, we can write 2x equals to Z. This is the first relation. How many of you understood this? I want all of you to respond here. Yes, yes, yes. Great. I'm coming to that. Let me finish this Ansh. Okay. First, you try to understand what I am talking about. Rubab, what is the doubt? Could you please, be specific here? Rubab, come again. What is your doubt? How did you find out? It's not 2. Rubab, it is Z moles. X, Y, and Z. It's not 2. Like I assume this X, Y. So this I have assumed it's Z. Fine. So it is clear, right? Now, could you apply this POAC for hydrogen atom? Tell me the relation for hydrogen atom if you apply for this, all of you. Very good, you'll get this. 2y is equals to 3z. Very good, guys. Now you see what we get from here. All of you concentrate here. I want to establish a relation among x, y, and z. Right? So we have 3z here. So can I write down this? All of you see this? 6x equals to 2y equals to 3z. Can I write down this? I want all of you to respond. Just think about it and tell me. Is it right? Can I write down this? All of you, please. Yeah. Aditi, did you get this? Shitesh, what about you? Ansh? Fine. Good. Now you see, if I divide this by 6, you'll be thinking, what is the point of all this we are doing? You'll understand this. Just give me 2 minutes. So this becomes x equals to y by 3 is equals to z by 2, x by 1. Okay, now we get this. Now I'm going to conclude this, so please be very careful here. X is the moles of nitrogen I have assumed. Y is the moles of hydrogen and Z is the moles of NH3. So if you balance this, not you forget all these things now, and you simply balance this reaction, you will get this 1, 3, and 2. Correct. Now the same ratio stoichiometric coefficient we are getting here. You see 1, 3, and 2. Means what? When you establish the relation like this and you write down in this way, okay, this denominator, whatever the number you have written here, these numbers are their respective moles in which they react. X is for N2, Y is for H2, Z is for NH3. Hence, we can say 1 mole of N2 reacts with 3 moles of H2 gives 2 moles of NH3. Did you get this? Okay, can I go ahead? All of you understood this? Okay. You'll understand it properly when you solve some questions. Okay. So let's practice some more on this. I want you to establish a relation among the number of moles of KClO3, the number of moles of KCl, and the number of moles of O2. I know you can do this by balancing the reaction. I don't want you to do that. I want you to establish the relation of number of moles of KClO3 that I'm assuming N1, N2, and N3. And I want you to establish the relation among N1, N2, N3 using POAC. Okay, Pradyun got this. N1 is equals to, N2 is equals to 2 by 3 N3. What about others? It's okay, not a problem, Shitish. Okay. Fine. So what we'll do, we'll apply POAC for the atoms, and also keep that in mind. We are applying POAC for atom, right? It is not for molecule. So we can apply POAC for potassium, and for that we'll get N1 is equals to N2. In short, if I write down, right? If you apply this for chlorine, what we get again? N1 is equals to N2. There is no need to do for these two because we are getting the same relation. If you apply for oxygen, you'll get 3N1 is equals to 2N3. Now easily we can establish the relation between N1, N2 and N3, N1, N2 and N3. So we can write 3N1 is equals to 3N2 is equals to 2N3. Okay. Further, if I divide this by 6, you see what we get. One common number, simplest common number we are taking. So we get N1 by 2 is equals to N2 by 2 is equals to N3 by 3. This means what we can write from this one, you see. N1 stands for KClO3. So we can say this, that 2 moles of KClO3 gives, N2 stands for KCl, gives 2 moles of KCl and 3 moles of O2. We can say this. Even if you check, if you place here 2, 2 and 3, you see the reaction is balanced. So basically by the use of this POAC, we are calculating the molar ratio only of reactant and product. In what mole ratio the reactant reacts, and product forms. Is it clear? All of you understood? No doubt. Okay. Now you must be thinking that we can easily balance these reactions, and we know how to balance a reaction. Then what is the point of this particular concept? Okay, like I said, sometimes what happens, they won't give you the complete reaction. Like in this case, try solving this question. And the question is, you see, iron, that is Fe, is extracted from its ore, Fe3O4, extracted from its ore Fe3O4. Calculate the amount of Fe produced by 1 gram of Fe3O4. This is the question. All the iron has been extracted. Okay, try this one. Anyone? Did you get the answer? No, it's not. It's not 3 gram. See, you try to understand this. Now, in this question, what happens? Obviously, reaction is not given, right? What do you know? What do you know? What is given in the question? That you have a sample. What sample? Sample of Fe3O4. And in this, there is some iron, some amount of iron present into this. That iron you have to extract. Means from this you have to take Fe out. Then what is the mass of iron you'll get from 1 gram of this sample? That is what the question is. So obviously in this, the reaction is not given. You cannot even write down the reaction, and then you cannot apply the concept of limiting reagent here because the reaction itself is not given. So this kind of question you will get where you have to use the concept of limiting reagent. Cool. So how do we do this first of all? So obviously we have iron. So we'll assume the number of moles of this, right? We'll assume the number of moles of this. And that is what I am assuming here. The number of moles of this is X mole. And for this, it is Y mole. Yeah, Pradyun, that is correct. Exactly right, Pradyun. Very good. So X mole of this, if you apply POAC, we'll apply POAC for what? We have only one choice, for Fe. So we can write 3x equals to y. Further, we can write x by 1 is equals to y by 3. Could anybody tell me what is the meaning of this expression that I have written here? What is the meaning of this? Exactly. 1 mole of X gives 3 moles of Y. And that is what we do when we have balanced chemical reaction. This mole of this gives this moles of this. So with POC, we get this idea only. So since the mass of Fe3O4 is given, so we can find out the number of moles. So X equals to the number of moles of Fe3O4, which is 1 given mass, divided by the molecular mass of Fe3O4, which is 56 into 3 for iron, plus 16 into 4 for oxygen, and that will be 1 divided by 232 moles. 232 moles, right? So 1 mole of this X gives 3 moles of Y. So these many moles gives the number of moles of Fe. Y is equals to 3 times 1 by 232. So this is the moles of iron we get. So this is the amount of iron, right? Which we can write the mass of iron divided by atomic mass of iron is 56. So mass equals to, we have 3 into 56 divided by 232. Could you tell me what is the amount, what is the value we get here? Point 0.72. So that is the answer for this question. 0.72 gram of iron we can extract from 1 gram of this sample. Now, did you understand the significance of this particular concept, POAC? Yes. Right. So if reaction is given, initial number of moles is Ansh, you see, if you can balance it, always do that. I am not denying the fact. But the point is you cannot balance this reaction. can't do that because you do not know what is the total reaction, what is the reaction given. Okay. Okay, we'll see some more questions based on this. See, whatever question I'm writing it down on the screen, you must copy down the question and then do the solution. Write down from 100-gram mixture of CO and CO2, carbon monoxide and carbon dioxide. All carbon are extracted to form acetylene. What is the formula of acetylene? If 35 gram of acetylene, C2H2, is produced, find the percentage composition of the mixture. Try this one. You cannot write down the equation, or actually, see, what is the information given? Just you write it down. We have a mixture of this. If the reaction is not given, don't try to predict the reaction. This plus this, and from this we are extracting carbon, and from this carbon we are getting C2H2. This is the information given in the question. So you don't need this, right? It's simply we have CO2 initially, and final thing is this C2H2. This is what given in the question. Now you see, you do not know the reaction. Initial number of moles is not given. Then you do not have any other option but POAC that you need to apply. Got it, Oro? Now what we do for POAC, you can do that. No, it's not 50-50%. Check your calculation, Oishik. $19.08. No, that is also not correct. Wait, I'll do this. See, in this question, okay. Try this. Try 2 more minutes. Okay, let's do this. See, so one thing is for sure here that you have to use POAC, correct? I hope all of you are agree with it, right? You don't have to any other option, right? You have to use POAC. Now, for POAC, we know that we have to assume the initial number of moles, okay? So let's assume that first, okay? I am assuming N1 moles of CO, N2 moles of CO2, and N3 moles of C2H2 we have. Okay, since we have to find out the percentage composition, means out of 100, what mass of CO is there and what mass of CO2 is there. That is what we need to find out. Okay, so if we have X gram of CO initially present, then CO2 would be 100 minus X because total mass I am assuming 100 since we have to find out the percentage composition. You can assume this as X and Y also. That is not a big deal. You can do that, right? I am taking X and 100 minus X. If you take X this and Y this, then X plus Y will be 100 because the percentage composition we need to find out. Okay. This mass of C2H2 is given in the question, that is 35 gram of it. Any doubt here? If you apply POAC, we'll apply POAC for which atom here? POAC for which atom? For carbon, right? So we are applying POAC for carbon because we have only one choice. There is no other way. No, Ashi, it's not correct. Again, you have probably you have made some mistake. So for total number of carbon here on the reactant side, we can say N1 plus N2. Any doubt in this on the reactant side? Yes, N1 plus N2 is equals to 2N3. Is it correct, guys? Number of atoms of carbon on the reactant side should be equals to the number of atoms of carbon on the product side. So this is the N1, N2, N3 is the number of moles. Number of moles, we can write down mass, that is X gram we have assumed, divided by the molecular mass of this. So molecular mass is 28. Here the molecular mass of carbon we cannot take because X gram, X is the mass of CO. N1 moles, N1 is the moles of CO, not carbon. That's why I have taken here molecular mass of CO, not carbon. Plus N2 is 100 minus X divided by molecular mass of CO2, which is 44. This is equals to 2 mass of acetylene is given 35 divided by molecular mass of C2H2 is 26. Just you need to solve this and get the value of X. That is your answer. How many of you understood this? Tell me the value of X, solve this. What is the value of X? Anyone? X value? $32.3. That's good. So X value is 32.3 gram because X is the mass. Out of 100, we have 32.3 gram of CO. So the mass of CO2 will be 67.69 gram approximately. So percentage composition is this only. Okay, fine. Next, write down calculation of percentage yield. We have just a formula here which we need to keep in mind, and you can solve the question. The formula of percentage yield is equals to actual yield divided by theoretical yield into 100. This is the percentage yield we have. Okay, this actual yield will be given in the question. And theoretical yield, the theory that we use, 1 mole of this gives this many moles of this. With that, the value that you find out, that is theoretical yield. Okay, this theoretical yield, this thing we calculate with the help of limiting reagent concept, POAC concept. We calculate this, right? This actual yield is given in the question. So our expectation is this, that we'll get this, but actually the product we are getting something else, some different amount we are getting. So yield is expectation divided by the actual amount that we are getting, the theoretical amount, which we calculate with the help of theory, right? Various concept of limiting reagent and this thing, principle of atomic conservation, into 100 is the percentage yield of this. Okay. To understand this, let's discuss this question. A reaction is given CaO plus 2 HCl. And this gives CaCl2 plus H2O. This is the reaction given. Now in this, it is given 1.23 gram. The question is 1.23 gram of CaO reacts with excess of HCl, and 1.85 gram of CaCl2 obtained. CaCl2 obtained. What is the, calculate the percentage yield of this? So this value that is given, 1.25, it is the actual yield given. This theoretical yield you need to find out, means by the concept of limiting reagent, whatever, you'll have to find out this theoretical yield, and then we have to use this formula to find out the percentage yield of this. Try this. Done. Tell me the answer. Anyone? What is the limiting reagent in this reaction? CaO is the limiting reagent. Okay. Number of moles of CaO is what? Excess of HCl is given. So there's no point of talking about like CaO here, the limiting reagent here. But the number of moles of CaO, is equals to given mass divided by the molecular mass of this, which is 56, and that is equals to what value it is? Okay, 84.3 you are getting. Fine. Number of moles is this we are getting. So 1 mole of this gives 1 mole of this too. So number of moles of CaCl2 is equals to 1.23 divided by 56. But since this value is given in mass, right? The actual yield is given in mass. So this also we have to convert in mass. So mass of CaCl2 is equals to the given number of moles into the molecular mass of CaCl2, which is 111. So when you solve this, you'll get 2.43 gram. So this value, which we calculate theoretically, we call it as theoretical yield. Hence, percentage yield is equals to actual is 1.85 divided by theoretical is 2.43 into 100. That will be, when you solve this, you'll get the value which is around 76% approximately. Did you understand this? So for this kind of question, you just need to know this formula, okay? And whatever question we have done so far, right? The calculation of the amount of product and all. Those concepts you have to use to find out the theoretical yield, and then use this formula, get the answer. Okay, all of you understood this? Yeah. Okay, the next part here we have determination of, write down, determination of atomic mass or molecular mass. Or molecular mass. And here we have to find out, we have to understand only one relation that we'll study under this law, DULONG'S and PETIT'S law. It is just a relation based on the research, okay, which is done by the two scientists named DeLong and Petit, okay. And this says what? No, it's not thermal capacity. It is specific heat capacity, not thermal. Specific thermal capacity or specific heat capacity, you can say. Specific term is there. So this statement to write down, in case of solid, it is observed that the product of atomic mass and specific heat capacity is almost constant. It is observed that the product of atomic mass and specific heat capacity is almost constant. Is it? Could you see my screen now? Guys? Yeah, it's fine now, right? Yeah. Okay. So this law, it gives us the relation of atomic mass into the specific heat capacity. Specific heat capacity. And the unit of specific heat capacity must be in CGS, okay? Calorie gram per degree Celsius. Calorie per gram degree Celsius. This is a unit. This is equals to, the product of this two is equals to a constant value, and that is observed to be around 6.4. So you just need to know this relation. This value, again, it will be given in the question. Given. Just you need to substitute it here and find out the answer. But you must need to take care of this unit here. See, specific heat capacity is the amount of heat required to raise the temperature of a substance. We'll get in gram only. You see, it is gram. Atomic mass will get in gram only. Right. So a specific heat capacity is the amount of heat required to raise the temperature of a substance by 1 degree Celsius. Amount of heat required to raise the temperature by 1 degree Celsius. This is the specific heat capacity. So nothing you need to know, much over here. Just this relation, every other data will be given. You need to find out the atomic mass by this. Done? Okay. Have you studied the concentration term, molarity, molality, all those? In 10th grade, have you studied the concentration term? Little, okay. So next we are going to discuss that only. Write down the concentration term. And this concentration term will be using in this concentration term will be using in the entire chemistry. Okay, we'll be using this in the entire chemistry. Okay, so that's why it is very important, the concentration term. Okay. Okay. Now, what is concentration here, first of all? Suppose you have water in a beaker or any solvent you can take. Suppose you have water in this beaker. Okay. Now, in this water or whatever solvent you have here, if you add some different compound into this, for example, suppose you are adding sugar crystal into it or salt or any other particles, right? Sugar crystal you are adding into it, right? So now you see there are two phases over here. One is liquid phase, that is water, right? One is liquid phase, that is water. And the other one is solid phase, that is sugar crystal or salt you place in. Okay. So there are two components here. One is sugar and one is water, right? So, and these two components forms a solution here. Forms a solution, we can say, or we can say this is here is a mixture, right? We'll talk about mixture also. Right, mixture. Now, mixture we have two types actually. One is homogeneous mixture and other one is heterogeneous mixture. Heterogeneous mixture, homogeneous and heterogeneous. Homogeneous mixtures are those mixtures in which we have only one phase present after dissolving it. Heterogeneous mixture means we have more than one phase. Like for example, we can prepare a heterogeneous mixture when we add sand into water. If you add sand into this, it won't get dissolved. Yes or no, guys? Sand won't get dissolved. It will get settled into this vessel, right? It will get settled down into this vessel. It won't get dissolved into the water here, right? So this is the heterogeneous mixture. But when you mix sugar into this or salt into this, after some time you cannot even identify the sugar crystal into this, right? Because the sugar crystal get dissolved completely into the water, and hence it forms a homogeneous mixture, right? So in this heterogeneous, what we can say here, we have more than one phases. One is liquid, other one is solid, that is sand. Homogeneous mixture are those mixture in which we have only one phase. That is one thing. Did you get this, guys? Any doubt in this? No? Okay. Now what happens? Suppose initially we have 1 liter of water you have taken, 1 liter of H2O, and in this you have added 10 gram of sugar. And then you have added 50 gram of sugar, and then 70, then 100, and so on. You are increasing the amount of sugar into it. Correct. So what we can say, 50 gram of sugar when you dissolve, so this solution, this mixture is more concentrated than this mixture, 10 gram mixture. Similarly, 70 gram mixture is more concentrated than 50, and so on we can go. Are you getting it? Yes, guys, I'm not getting any response. Correct. Now there are two components into this. Okay, concentration term you understood. Like concentration term specifically you understood. What is the concentration here? But there are two components. We are more interested in this homogeneous part, right? Now there are two components into this. One is sugar, other one is water that you are mixed, right? So one part of this will be the solute and other one is the solvent. Have you heard this term, solute and solvent? Right. How do we define solute? Could you tell me? How do you define solute? Like in this example, what is solute, what is solvent? Sugar is solute and water is solvent. So solute is something which get dissolved into the other substance. Can I say that? Substance present in a small concentration is solute. Possible, can say that. Okay. Can solvent be solid also? Can we take a solid substance as a solvent? It has to be fluid. No, it's not always true. See, actually, solute and solvent term we define with respect to their amount present in the mixture. Like suppose if you have 1 kg of sugar, right? 1 kg sugar you take and you add 0.1 ml of water into it, or 1 drop of water, 10 drop of water into it. Okay, in that case, this sugar will be the solvent and water will be the solute. So solute and solvent is always defined by their relative amount present in the mixture. So we always say solute is the component of a mixture. I'm talking about mixture now, not solution. In that case, if the relative amount is equal, in that case, we can take either of the component as solvent or solute. Any one we can take. That's not a problem. Right? So solute we always define by it is the component of a mixture which is present in lesser amount. Write down here. It is a component of a mixture which is present in lesser amount, that is solute. Solute always in lesser amount. Solvent always in more amount. Always in more amount. Correct? Solute can be solid, liquid, or gas. Solvent can also be solid, liquid, and gas. In this way, if you see, there are 9 types of mixture possible. If solute is solid, solvent can be solid, liquid, gas. If solute is liquid, solvent can be solid, liquid, gas. If solute is gas, solvent can be solid, liquid, gas. All 3 combinations are there, 9 combinations are possible, hence 9 types of mixture possible. Is it clear? Right. I am talking about mixture now. Have you heard about a term that is called as solution? What is a solution? What is a solution? Is there any difference between solution and mixture? No, solution is a homogeneous mixture. Correct, Kshitij. Mixture can be heterogeneous or homogeneous, but solution is a homogeneous mixture where the concentration is always equal at each point, at every point actually. You can take an example of suppose like Coke, Pepsi, Coca-Cola, anything, right? You have a bottle, 2-liter bottle of Coke, right? When you place this into 5 different glasses from the same bottle, 5 different glasses, then the taste of all these 5 glasses will be equal. Like, you know, the Coke that is present in 5 different glasses, the taste will be same, right? There's no difference in the taste, right? So that's what we can say, that solution, why the taste is same in all the glasses, because their concentration is same everywhere. If concentration is same, then the solution is said to be homogeneous. Okay, one phase plus concentration is same at all point. Means if you take, suppose you have a mixture of sugar and water over here, if you take 1 spoon of sample from here, you'll have the same test as we have the test at this point, or sample at this point, or any point if you take. If you have the same composition, test means same composition we have at every point, then the solution is said to be homogeneous. This point, any point. From anywhere you pick the sample, you have the same, exactly same composition, then the solution is said to be homogeneous. Mixture is said to be homogeneous. So homogeneous mixture is solution. Solution has two components. One is solute, like I said, which is present in lesser amount, and other one is solvent, which is present in more amount. Did you get this? In solution, solvent is liquid, but it can be gas, it can be solid also. We have a chapter in 12th grade. The name of the chapter is solution itself. We'll discuss that chapter in 12th grade, okay? But did you understand this? Solution has two components, solute and solvent. Solution is homogeneous mixture. What is the meaning of homogeneous mixture? The composition at every point will be same, right? We have many examples of homogeneous mixture, right? Coca-Cola, Pepsi, all these are homogeneous mixture. Air is a homogeneous mixture. Air. Why? Yes, it is not an ideal situation. Air is not a homogeneous mixture. Correct? So that is what the meaning we have here. So solution has two components. Now coming back to this concentration term part over here, solution has two components, solute and solvent. Now you see concentration term we also have understood that if the amount of solute you keep on increasing, the solution is said to be concentrated, becomes concentrated. Yes or no? Amount of solute you increases, the solution becomes more concentrated. Is it right? More amount, more concentration, correct? So how do we define this concentration actually? See, for solute, we can take the amount of solute, we can take in kg, we can take in gram, we can take in mole, anything, right? Similarly, solvent amount, we can take in gram, we can take volume of solvent also. We can say this gram of solute present in this volume of solvent. We can say this gram of solute present in this mass of solvent. So there are two terms over here. One is mass of solvent we can take. One is volume of solvent we can take. Another thing what we can take, for solute also we can take mass, amount. We can also take volume of solute present into this. So all these possibilities we have. We can say 1 ml of this thing, oil, not oil we cannot take. Any liquid which can form a homogeneous mixture with other liquid. So 1 ml of one liquid present in 10 or 100 ml of other liquid and forms a homogeneous mixture, right? So we can define the amount of solute present in any solution in terms of mass, mole or volume. We can define the amount of solvent present in any solution in terms of mass and volume, correct? So if this thing varies, whether you are taking mass and gram of it or volume of it, you'll get one concentration term, mass of it and volume of it, another concentration term, mass of it, another concentration term, volume of solute, volume of solvent, another concentration term. So based on this composition, this combination actually, we have defined different concentration term. Is it clear? Did you understand this? Right. Now the various concentration term we have. The first term you write down, which is molarity. The first concentration term we have, molarity. See, molarity is represented by this. Molarity is represented by capital M. This is molarity, capital M. And it is defined as, write down, It is a number of solute, number of moles of solute present in 1 liter of solution, right? 1 liter of solution. So solution 1 liter, moles of solute. So the formula of molarity is, it is a number of moles of solute divided by volume of solution in liter. It must be in liter, right? If it is not in liter, then we have to convert this into liter. Okay. So if the volume of solution is given in ml, then what we can write? Number of moles of solute divided by the volume of solution. If it is given in ml, then we have to convert this ml into 1000 and we have to multiply 1000 here in the numerator. Okay. Number of moles into 1000, it becomes the number of millimoles. But a volume of solution in ml. One milligram. See, 1 milligram, if you convert into gram, what you will write? Yes, right, correct. 1 mole into 1000 is 1 millimole. So this is the 3 expression, same expression only, different units we have. So now you see, if molarity is given, so if you multiply molarity by volume of solution in liter, you will get number of moles of the solute. Okay, so this is again the another formula to find out the number of moles. Number of moles equals to the concentration molarity into volume of solution in liter, right? Number of millimoles, if you need to write, it is equals to molarity into volume of solution in ml, right? Number of millimoles, molarity into volume of solution in ml. So by this formula also we can find out the number of moles, number of millimoles. Is it clear? Okay. Now you see molarity here. Molarity has volume present, like volume term involved into this. That's why molarity is the temperature dependent term, right? It is temperature dependent concentration term. Volume changes with temperature, right? Hence, it is temperature dependent concentration term. In fact, all the concentration term which has volume involved, those are temperature dependent concentration term. Understood this? Okay. The another concentration term we have, that is molality. Next, write down molality. We'll finish this and then we'll take a break. Just 5-10 more minutes. Molality. Okay. Write down. It is the number of moles of solute present in number of moles of solute present in 1 kg of solvent. See here we have solvent, it's not solution. 1 kg of solvent. So if I write down the relation here, molality represented by small m, it is equals to the number of moles of solute. In the numerator, we always have solute by mass of solvent in kg. Right? If the mass of solvent is given in gram, then what we can write? Moles of solute divided by mass of solvent in gram, but this gram you have to convert into kg, so you will multiply by 1000 here. And similarly it becomes millimoles by mass of solvent in gram. Done. Finished this one, guys? So you see here, there is no volume term involved into this. That's why molality is independent of temperature. Independent of temperature. Okay. Fine. So we'll see some question based on this, a two term, that is molarity and molality, after the break. Okay. Hello, can you hear me, guys? Yes. We'll resume the session at 6:35. Take a break now. Hello guys, can you hear me? Yes, you will have test. Most probably, no, you have test. CAMON test, you have CAMON, that we call it a Symptom Academy monthly test. Okay. Every month you will have one. Most probably you will have this next month. Okay. Mid of the next month or in the last week, maybe like that. You'll get to know about it. Okay. Now, guys, few things I wanted to discuss with you apart from this, the academic part. This is the lecture that we have here. That is regarding the syllabus that we have, okay, of the entire 11th grade. Okay, I was about to discuss this in the beginning only, but I forgot. So I am discussing this here. Quick few minutes, and then we'll move on to our topic, right? You see, first of all, you are going to have the entire, the curriculum has been designed for 11th grade for you is like this. You're going to have 14 chapters in 11th grade for chemistry, right? 14 chapters in 11th grade you are going to have. Okay, we are doing this right now. We are doing this. Some basic concepts of chemistry. In some book, they have written this as mole concept also. Mole concept. So we are doing this right now. Structure of atom, physical chemistry. This two chapter belongs to inorganic chemistry. Inorganic chemistry. Okay. Hydrocarbon, some basic principle techniques. This one, these two belongs to organic chemistry. Organic chemistry. Right? All other chapters, these three chapters here you see, these three chapters are again inorganic. So apart from all these 5-7 chapters that we have, all other chapters belongs to physical chemistry. Right? This is physical, 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 physical. All these are physical chemistry. Right? So you can see in 11th grade, we have 14 chapters and 9 of these 14 chapters are of physical chemistry. Okay. So most of the portions of physical chemistry, almost 80% of the portion, we are going to cover in grade 11, right? In grade 12, we are going to have 5 chapters of physical chemistry. All 5 are important. 5 chapters you will have of physical chemistry. Okay, we are doing this this particular chapter. Okay, in this chapter you see this ionic equilibrium. This equilibrium actually it contains 2 chapters, chemical and ionic. So chemical equilibrium is, we can say, it is the easiest chapter of physical chemistry, but ionic on the other hand, it is the toughest one in physical chemistry. Okay, all other chapters are moderate. Okay, it is not very easy, it is not very tough. Okay, you can do questions from this. Okay, so what I am planning here, that this chapter we are like I said, we are going to study this chapter in two different portions. I've told you in the first class, mole concept 1 and mole concept 2. So mole concept 2 contains the concept of redox reaction, means the entire redox reaction will cover in mole concept 2, right? This entire redox reaction will cover in mole concept 2. So why I'm telling you this, because there are different names, right? But we'll cover all the portions. Okay, you don't have to worry about. Now in this, see, in all these chapters, you see there is nothing called a chapter here, GOC, which stands for General Inorganic Chemistry. General Inorganic Chemistry, right? This actually, you understand this, it is the backbone of entire organic chemistry. If you do not understand it properly, okay, this organic chemistry will haunt you the entire year. It's not GIC, it's general inorganic I have written by mistake. It is general organic chemistry, right? It's GOC. Okay, so this is very important to understand, otherwise the entire organic chemistry will haunt you in the 12th grade, right? So, and I can understand few of you are going to write KVPY also this year in November, I guess, right? Is it? How many of you are planning for KVPY this year? Yes. So I can see many of you are writing KVPY this year. So in KVPY, there is a major portions of organic chemistry, right? So anyways, this GOC we are going to discuss in the last, like month of this year, like November, December. But I'm planning to take this up right after this chapter, mole concept 1. Okay. Once you understand this, little bit things you can go through on your own, right? In school, they will never teach you this chapter. Like, they will never teach a chapter called GOC, General Organic Chemistry, because it is not given in NCERT, right? Few concepts are given here and there in the book, but there is not a separate chapter called General Organic Chemistry. So I'm planning to take this up right after this mole concept 1, okay, so that you will have a base in organic chemistry. Nomenclature we already have done. Once we finish this, few things you can read on your own, right? I can give you those materials, PDFs, so that you can read on your own and solve questions, right? So that is what my plan is. After this small concept in which few things are left, I will be starting general organic chemistry. Very important chapter this one is, right? So we'll do this. Few things like you have here, periodicity and chemical bonding. After this chapter, these two chapters, okay, you can study few chapters of inorganic chemistry on your own also, right? Here we'll discuss few terms in these two chapters which you are going to use in other chapters of chemistry. So once you are not aware of those concepts here in these two chapters, you won't be getting those concepts in the other chapters, right? Suppose if I discuss something over here, then the chapters like hydrogen, S block, P block, you can do on your own, because here we have only theory, right? I am not saying that I won't teach. Obviously I'll teach, but if you want to go a bit ahead, right, then after doing these two chapters, you can go through for these chapters. Okay, so that's why my plan is I'll finish this chapter mole concept, and then I'll be taking up this general organic chemistry. Is it fine? Okay, so this is the entire plan of your 11th grade we have. Okay. into this particular chapter so that you can understand concepts properly, and then we'll use those concepts in the various chapters. Okay, state of matter is, it is also a big chapter, but not that again, but a little redox will cover here only. It is an easy chapter, you don't have much into this. These three are easy chapter. Okay, and environmental chemistry we don't have much, uh, a weightage of this chapter in the coming exam. Okay, so this is it for the entire 11th grade. We'll follow this plan. Okay, so I have told you what we are going to do in coming 2-3 months. Okay, so let's start with our class, whatever we were doing. We were doing this thing, concentration term. Concentration term, we have discussed two concentration term, that is molarity, molality. Apart from this, we have another concentration term, normality, formality, weight by weight percent, weight by volume percent, volume by volume percent, parts per million. Okay, these are various different concentration terms we have, but the most commonly used concentration terms are molarity, molality, and normality. So you have to be very careful with these three terms. How do we use this? What all things we can find out from these concentration terms? Normality, I am not doing it now. We'll do that normality part in mole concept too, because to understand normality, you should first understand the concept of equivalence. Okay, and concept of equivalence, it will take some time, so I'll take up that later after finishing this. Okay, in mole concept 2, where we finish the redox part also, redox reactions also. Okay, so let us discuss some questions on this molarity, molality that we have already discussed just now. Write down this question. Calculate molarity of NaOH. First question. First question. If 100 gram of NaOH present in 500 ml of solution, 5 mole of NaOH present in 700 ml of solution. I'm giving you very basic questions now. Third one is 50 millimole of NaOH in 50 ml of solution. Try this. Okay, done. Point 8, 7.14 and 1. Okay. So the first one, 100 gram of NaOH. So molarity is capital M. 100 gram, 100 divided by molecular mass of NaOH is 40, divided by 500 ml is there, so into 1000. So it is 5 molar solution, right? Five molar solution. Second one is molarity 5 mole of NaOH. So mole is already given, 5 divided by 700 ml into 1000. So it is 7.1 molar. Third one is 50 millimole. So 50 millimole divided by volume of solution in ml, that is 50, 1 molar solution. Just formula based, right? One question you write down. What should be added to 2 liter of 2 molar NaOH solution, 2 molar NaOH solution, so that the molarity becomes first one 2.5 molar and second one 1.5 molar. These are two different questions. Okay, try this one. Done. What is the answer? Tell me. $120 Oh, what are you getting? 120 gram and 40 gram. What we need to add? 120 gram of what? Acha. NaOH. Okay. Both, I think both are not correct, Aditi. Yes, that's right. That's right, Ansh. 1 mole of NaOH and 0.66 liter of solvent you need to add. Okay. See, actually, the question is about what should be added, right? Means we need to add something into this so that the molarity in the first case increases and then decreases. Okay. So we know the formula of molarity. It is the number of moles of solute by volume of solution in liter, right? Now, you see, this molarity is directly proportional to the number of moles of solute and inversely proportional to volume, right? So in the first case, if you have to increase molarity, we can do two things. Either we can decrease volume or we can increase number of moles, right? We can do two things to increase molarity. Either we have to decrease volume or will increase number of moles. But to decrease volume, what we need to do, we have to take that solution out of that solution, correct? That is not possible because the question is about what should be added. So we cannot remove anything. We can add some solvent or moles into it, but we cannot remove anything into it. So only option is left with, we have to add something into it. So once you add number of moles, molarity will increase. Once you add volume, molarity decreases, correct? So in the second case, what we have to do, we have to increase the volume of solution in order to decrease the molarity from 2 to 2.5, 2 to 1.5. NaOH is solid here. Okay, so in the second case, if you have to decrease molarity, we have to increase the volume. In the first case, when you have to increase the molarity, means we have to add some solute into it. Okay, so what I have assumed for the first question, I am assuming n moles of solute has been added so that the molarity becomes 2.5. So molarity is equals to what we can write? Number of moles, initially it is what? Initially it is molarity into volume. So we have 4. So initially we have 4 moles. And in this we have n moles of solid also we have added. Divided by volume won't change. It is 2 only. It is 2 only, right? So this volume is equals to, this molarity is equals to, it is given. It is 4 n by 2 is equals to 2.5 according to the question. When we add n moles of solute into it, its molarity increases to 2.5. That is what our assumption is. So this is the relation. Now when you solve this, you'll get n is equals to 1 mole. Means what? To increase the molarity from 2 to 2.5, we have to add 1 moles of solute into it. Volume won't change because volume NaOH is solid, right? So we are adding solute into it, right? The solvent particle is not changing, and you cannot change both. That is assumed to be constant. No, the amount of solvent is same. That is not changing. You have taken, suppose, 5 liter of it. In that, you have added 1 mole of NaOH, then another 2 mole of NaOH. Still, it is 5 liter only. That is what we are taking. It is not like the volume that is, occupied by the solvent. It is like the volume of solvent that you are taking. Okay. And if you change both, then in that case, you won't be able to solve this question. You cannot change both, right? So we have taken some amount of solvent and we are adding solute into it like that. Okay. So in the first case, we have to add 1 moles of solute in order to increase the molarity from 2 to 2.5. Now in the second case, what we have to do? We have to decrease the molarity. It means we have to increase the volume. So what I have assumed that V liter of solvent we have added into it, solution we have added into it. So what is the molarity now? Molarity is 1.5. That would be equals to, again, the solute number of moles won't change. Initially the volume was 2 and V liter we have added. So when you solve this, we'll get 1.5 V is equals to 1. So V is equals to 10 by 15, and which is 0.66 liter. Means we need to add 0.66 liter of solution so that we'll have the molarity as 1.5 molar. Did you understand this? Okay, no problem. Another one. See, this question that I am going to give you, it is a very common question, and they have asked this question. Means I'm not talking about the data, but the pattern is exactly same. And this kind of question they have asked in JEE, NEET, other exams also KVPY, BITSAT, all exams they have asked this kind of questions. When the question is calculate molality of 4 molar NaOH solution whose density is given, that is 1.4 gram per ml. Molality we need to find out. Molarity is given, density of solution is given. Oh, I'm sorry, I was muted somehow. Yeah, it's fine now. Can you hear me? Yeah, by mistake, I was on mute. Yeah, correct. 3 point something. Yeah, I was talking and I was on mute by mistake. Anyways, so 3 point something is the correct answer. I think 3.2 is correct. Okay, 2.8 is not correct. 2.85 is not correct. I think 3.2 is the correct one. Yeah, approximately that is correct. I'm not very sure with the answer, but 3 point something is there. Anyways, so what I'm going to do, I'm not going to solve this question directly. We'll obviously see this question, but I'm discussing one concept here, how to get the relation of molarity, molality, and density. Are you getting it? I'm trying to establish the relation of molarity, molality with the density of solution. Usually what they do, they'll either give you molality or molarity here with the density of solution. And they'll ask you to find out the other concentration term. Like in this case, they have given molality, they have given molarity, and they're asking you to find out molality if the density of solution is given. They can also ask you calculate molarity if this solution has density this. Okay, so either molality or molarity will be given, and the other term they will be asking, right? So how to do this? First of all, we know the formula of molarity is this. Molality is again moles of solute divided by, it is the mass of solvent. Solvent I'll write down only in kg. Unit is also very important here. Okay. Right. So what we know the mass of solution is equals to what we can write? Is equals to mass of solvent plus mass of solute, because solution has two components, solvent and solutes. It is made up of these two. So whatever the mass of this plus this, that would be the mass of solution. Right. We need to find out the mass of solvent. So mass of solvent is what? Mass of solution minus mass of solute. So mass of solvent is equals to mass of solution minus mass of solute. Solute will be mentioned in the question. Like here it is NaOH mentioned. Okay, solute will be mentioned in the question. Here it is NaOH mentioned. What is the mass of solution? Can we write down this as density of solution into the volume of solution? Mass is nothing but density into volume. So it is density into volume of solution is the mass of solution minus mass of solute is what? Molar mass of solute into what we can write? Into what we can write? Mass of solute is not number of moles is equals to mass divided by molecular mass. So this into number of moles of solute. Okay. Okay. So what I'm trying to find out, I'm trying to equate number of moles of solute in terms of molarity and volume of solution, in terms of molality and solvent of solution, solvent of the mass of the solvent, right? So number of moles of solute we can write molarity into volume, and number of moles of solute we can write molality into mass of solvent into kg. And mass of solvent we can express like this, and then we can do some cross multiplication. You can simplify that expression, you will get the relation of molarity and molality. Okay, this is the idea we have behind this. Mass of solvent we can represent in terms of molar mass of the solute, which we know already, moles of the solute, which we have in the numerator, Density is given, volume of solution we have, right? Which will get cancelled afterwards. So how we'll derive the relation? The idea is this. Now, how do we derive? You see, for that, you see what I am assuming here. I am assuming the volume of solution. Okay, unit is also very important. That's why I'm writing it down. Of solution is V ml. I am assuming ml. Okay, molar mass of the solute. Molar mass of the solute, which will be given in the question. Like here, it is NaOH given. I am assuming X gram of it. Okay, molarity. Molarity. I am assuming you all must copy this down. But first, you see this. What we are doing. M is the molarity, and this is mole per liter. Obviously, the unit is mole per liter. Molality. Molality is what? It is again M mole per kg. That we already know. The unit is mole per kg. And the density of solution. This is important here. Density of solution is D gram per ml. If any other unit is given, you have to convert this into gram per ml. Then you can use this particular expression, which we are going to get after this. First of all, could you tell me what is the mass of solution? It is D into V, correct? Density of solution into the volume of solution, because it is the density of solution, right? This is for solution. So solution and solution we can multiply. D into V gives you mass of the solution. Now molarity is what? Capital M is the molarity. It is the number of moles of solute by volume of solution. Volume of solution is V, that too in ml into 1000. So what is the number of moles of solute from this? We can find out mv by 1000. That is what I said. Number of moles we are going to equate mv by 1000, where m is the molarity. Number of moles of solute. See, the number of moles of solute, we can further write it as mass divided by molecular mass, capital M, molar mass, right? So number of moles is this, mv by 1000. We'll substitute here. So mass of solute is equals to what we can write? Number of moles is mv by 1000. Molar mass, I am assuming it as X, right? So it is mv into X by 1000. Is it clear? Till here it is fine. This is the mass of solute. And why we are calculating mass of solute? Because we need to find out the mass of solvent. And mass of solvent is mass of solution, that is D into V, minus mass of solute, which is mvx by 1000. How many of you understood this? Because molality, for molality, we need to find out the mass of the solvent, correct? So our objective is to find out the mass of solvent. So mass of solvent is mass of solution minus mass of solute. Mass of solute will find out with the help of molarity and the formula of number of moles. Now just you need to simplify this. V by 1000 if you take common in order to make it in a proper way. 1000 D minus mx, let it be. Now molality is equals to what? Number of moles of solute, okay? So N of solute divided by mass of solvent is this, which is V by 1000 into 1000 D minus mx into 1000, because the mass is given in gram, okay? Okay, now you see this. I just want to finish this in this particular page only. So I'm replacing this number of moles of solute by this, which is M into V by 1000. Now you see, this V will get cancelled, this 1000 will get cancelled. So what we are left with? We are left with 1000 m, where this m is the molarity, divided by 1000 d minus mx. What is this x? Tell me. Any doubt? Did you understand this? See here, what you have to keep in mind, the density which is given in the question, that must be in gram per ml. Okay, if not, then you have to change it, right? M, capital M is the molarity, X is the molar mass of the solute. Here in the question, the solute is mentioned, and that is NaOH. Density is also given. So we are going to use this formula to solve this question. You see this? What is the molarity given in the question? What is the molarity given? Molality is equals to, we have 1000 m divided by 1000 d minus mx. What is the molarity given in the question? Molarity is 4, right? So 1000 into 4 divided by 1000 into density is 1.4 minus molarity is 4, molecular mass of NaOH is 40. Just you need to solve this, you will get the answer. So it is 4000 divided by 1400 minus 160. That will be 4000 divided by 1240. Answer is 100 by 31. That is 3.2 molal solution. How many of you understood this? This is very important. Okay, just you need to know this relation, right? You can do this kind of question. Okay, did you copy all these derivation? Did you copy this one? Please copy it down, all of you. Let me know once you finish this. No, derivation they won't ask. It is not going to be the subjective one. Derivation they are not going to ask. But yes, suppose if you forgot the formula, then you should know the idea how to derive this. That's why I have done this. But derivation they are not going to ask. It will be a multiple choice, question. Okay, only one answer will be there. MCQs. Okay, so you don't have to memorize the derivation. Done, all of you? Yes, Ritesh. Yeah, there are many other ways you can do this. There are many different ways you can do this. Just a one method. You understood, right, Shitish? Correct, fine. You see, so these two concentration term we have. Apart from this, we have another concentration term, and it's a simple formula, not very important. I'll write down the formula here. The next one is percentage weight by weight. Percentage weight by weight. And then we have percentage weight by volume. Weight by volume. Another one we have percentage volume by volume. Okay, so percentage weight by weight, you see, in the numerator, we always write solute, and in the denominator, we'll write solution. So we have this weight by weight. So in the numerator, we have solute. So since we have weight by weight, so mass of solute in gram divided by the mass of solution. Solute by solution always. Whatever unit we are taking here in the numerator, same unit will take over here. Gram and gram into 100, not 1000. Here we have weight by volume. So the first term will go with solute. Second will go with solution. So this will be mass of solute in gram again, divided by, since we have volume here, so volume of solution. Volume of solution in ml into 100. Here also what we should write? Volume of solute in ml divided by the volume of solution in ml into 100. This is the formula we have. So first term that we have written, it is always goes with solute in the numerator, and the second term will go with solution in the denominator. Is it clear? Finished? One more term we write down here, that is mole fraction. Mole fraction represented by X. Mole fraction is represented by X. Okay. Now suppose we have a mixture of suppose 3-4 gases here. A, B, C, D, we have mixture of this. Okay. So mole fraction, how do we define? X equals to mole of one component divided by, it is fraction, right? So divided by the total number of moles. Mole of one component divided by the total number of moles. correct? So suppose you have to define the mole fraction of A. So XA is equals to what we can write? Number of moles of A divided by the number of moles of A plus B plus C plus D. Similarly, mole fraction of B is equals to NB, number of moles of B divided by number of moles of A, number of moles of B, number of moles of C, and number of moles of D. And then number of moles of C, mole fraction of C is number of moles of C, again A plus B plus C plus D, N of D. And mole fraction of D is equals to number of moles of D divided by Na plus Nb plus Nc plus Nd, right? So in a given mixture, if you have 4 different components or any number of components, if you have, sum of the mole fraction of all components will be equals to what? If you add all these, Xa plus Xb plus Xc plus Xd, the sum is always equals to 1. Okay, so sum of the mole fraction of all the components present in a mixture is always equals to 1. Percentage weight by volume. So mass of solute by volume of solution. No, we cannot say that. Mass of solute. I didn't get you, Shitesh. What you have written? M into molecular mass of solvent into 1000, is it? M is the molarity. We can write that way also. You see this. Achha, M is the molarity. So percentage weight by volume is mass of solute divided by volume of solution in ml into 100, right? We can convert this into molarity. Mass of solute, we can write moles into molecular mass, moles into molecular mass of solute divided by volume of solution into 100, right? Now, if you want to convert this into molarity, then volume of solution is in ml. So what I am doing here, I am just multiplying this by 1000. Here I am multiplying by 1000 and dividing by 1000. So you see this moles into this by this is molarity. So we can write molarity into molecular mass divided by 10. This we can write. Molecular mass, this we can write. Yes, so this molarity is for solution, molecular mass of solute. And that means you can simplify this. That's not a big deal. The basic definition is this. Got it? Okay guys, so we'll wind up the session here. Okay, you have assignment is given on LearnList. You can solve those assignment. Okay, I'll share some more assignment on the group. Okay, PDF I'll share. Thank you guys. Take care. Bye-bye.